Okay, so we're going to be looking at calculating density this evening. We're going to be looking at calculating the density of these solid objects. And we're also going to be looking at calculating the density of some liquids. And the liquids are going to be solutions that we ourselves are going to make tonight. Hopefully you got that answer right in the quiz. It's table sugar that you were supposed to bring for this particular one. We're going to be using about 250, 300 grams or so, depending if you spill any. So let's look at some of the background here. So this basically just took this directly from the instructions. Hopefully this won't be new to you. One of the things we learned originally in one of our first classes are what's the difference between an intensive property of a substance and an extensive property of a substance. Density is an intensive property. Can anyone tell me what that means? What does that mean when if some property is intensive?
It does not change with quantity in its intensive property.
Excellent, that's right. I could have a gram of material, I could have a pound of material, I could have a ton of material. The density of it doesn't change. Whereas the mass of it changes and the volume of it changes. But interestingly, the ratio between that volume and that mass stays the same. So we call that an intensive property that's derived of two different units, as I said, mass and volume. So we want to figure out tonight for these what the ratio is between the mass and the volume, and we're going to do exactly the same thing with some liquids. So yeah, if anyone hasn't found their balance yet, hopefully be able to find it soon, because it is absolutely essential. And the units we're going to be using are the sort of the typical units for density. And the standard unit for density is grams over cubic centimeters. That is pretty much the standard for density. When you look up the density of anything, it's typically given in grams per cubic centimeter. And the reason is that what's the density of water? Anyone remember what the density of water is? That's something you're going to be measuring tonight, actually. What do we expect to find when we calculate the density of water?
One gram.
I'm sorry?
1 gram per cubic meter.
That's right, exactly. Yeah, at 25 degrees Celsius, the density of water is 1.00 grams per cubic centimeter. And so basically, since water is so important and so ubiquitous, that we basically compare everything to water. Is it going to float on water? Is it going to sink in water? That's why when you mix oil and water together, the oil floats on it because its density is less than that of water. And when you throw something heavy in there, like our aluminum cylinder, that is going to sink because its density is greater than water. It's not the mass of the object that matters, it's the density of it that matters. And so this unit of cubic centimeters, we're going to be calculating cubic centimeters with our solid material, but we're not going to be using cubic centimeters when we're dealing with the liquid. What units are we going to be using when we deal with the liquid tonight?
Milliliters.
Milliliters, right. M for milli, which means 1/1000th, and L for liters. So that's 1/1000th of a liter. So what's the relationship between a milliliter, and a cubic centimeter. Since we're dealing with, since we're going to be dealing with the solids having a volume in cubic centimeters, and the liquids with volumes of milliliters, what's the relationship between these two?
They're equivalent.
They're exactly the same. That's right. In fact, if some of you are in the nursing field or in the medical field at all, you know that sometimes you see syringes with markings of cc's, right? I think they still have cc's sometimes on syringes, probably not as much as they used to, but syringes used to come basically almost entirely in cc. So you'd be giving someone like a 1 cc injection or a 2 cc injection or whatever it was. And now on syringes, basically you just see mLs instead. And the reason is they're exactly the same thing. cc actually stands for cubic centimeter. So they're precisely the same thing. So we can directly compare the two. So the very first activity will be determine the densities of these solids. So we'll be able to do this before putting our goggles on and going into it. So we're just going to take each one of them, and hopefully you found your ruler in there. Now on the ruler, I don't know if you'd be able to see this very well, but on the metric side, since we're going to be using the metric side always, the larger units are centimeters and the smaller units are millimeters. So you can see in between like 1, 2, 3, and 4, those are centimeters. And there's 10 markings inside each centimeter. And we know that there are 100 centimeters in 1 meter. There is 1,000 millimeters in 1 meter. And so these small units are millimeters and the large ones are centimeters. Since we're going to be using cubic centimeters, you have to make sure that when you measure the height and diameter of these things, that you use centimeters. It's real easy to use millimeters because, I mean, you know, they're right there. You can see the smaller units we're going to want to make an accurate measurement as we can, but we need to be able to convert it back to centimeters, because when we measure the height in centimeters and the radius, which is here to here, we're going to multiply radius times height. They're all going to be in centimeters, so our unit should be centimeters cubed when we're done. And then we're just going to measure the mass, divide the mass by the volume, and we'll get the density of each one. So I think the densities are given, like what they should be for each one. For the acrylic, should be a little more than 1 gram per cubic centimeter. The polyethylene, which is the white one here, should have a density of around 1, maybe a little bit more. And aluminum should have a density of somewhere around 2.7 grams per cubic centimeter. That's the actual density of aluminum. So when I did my calculation last night, it was a little bit off. Don't feel bad if you don't get it exactly, because trying to measure these things is really, really hard. And if you make even just a small error in measurement, when we cube something, it's going to, you know, actually increase the error. So, I mean, if you're within 20%, that's pretty good. One thing I want to point out when we're doing our measurements, you remember I've sort of been harping on and on about when you make a measurement, the last digit of your measurement is an estimate by you. And that's that will especially be the case here, because when we're doing this measurement, you can see that when we line up, when we're trying to get that measurement correct, that it's not going to be, it may not line up exactly on one of the lines. It may be in between one of the lines. And so we may measure the height as maybe, let's say, 12.2 millimeters high. So it's a little longer than 12 millimeters, but it's not quite. So these two are significant digits because it's definitely greater than 12 and it's not 13 millimeters. We can clearly see that. But this number is an estimate made by you. So if you think it's right in between 12 and 13, you would write 12.5. If it's right on the line, if you think it falls dead on the line, would you write 12 or would you write 12.0? Which one should you record in your report? Should you write 12 or 12.0?
12.0.
12.0, exactly. You should have 3 significant digits, because remember, even though this number is an estimate, it is significant because you can see with your own eyes that it's not 0. If it was right on the line, it would be 0.0, but it isn't. So now it's up to you to figure out, well, how much do I think it's past the line? If I think it's just past, it could be like 0.1 or 0.2 or 0.3 maybe, but that's your call. And that is also a significant digit, okay? And that'll also be true when we're measuring the volumes of our solutions tonight. You should get 3 significant digits in that measurement as well. So these are the 6 solutions you're going to be making tonight. So have this table in front of you when you're constructing, when you're making your different solutions, because it tells you for each one of them, you want 50 grams of water. Now make a note of that. It doesn't say 50 mils of water, does it? No, it says 50 grams. So we're actually going to measure 50 grams of water. And then we're going to measure sucrose, which is a solid. So I'll be showing you when we get together how we measure the mass of a liquid, how we measure the mass of a solid. So we're going to be making 1, 2, 3, 4, 5, 6. These are called standard solutions. Why are they called standards? Because we are going to be making them, and we are going to be using these to figure out what the density of each one is. So once we have the density of these solutions, that we know what the percentage of sucrose is, we can use that information to figure out, once we have the density of our unknown, our apple juice or energy drink or whatever it is we're going to use. Once we figured out what the density of that is, we can refer back to the data we've collected here with these standard solutions, and then figure out what the percent sucrose is of our unknown. Okay. So we should have 6 cups and label them 10%, 20, 30, 40, 50, and 60. Now, these are going to be a little bit tricky. These last 3 are a little tricky because we have a lot of sugar and compared to water. And so you may have to heat them gently. So I would suggest microwaving them for like 5-10 seconds at the most, and then stirring them to get them into solution. That last one is going to be a bear. The 60%, that one's tricky to make because that's a lot of sugar. in water. That's going to be quite dense. Okay, so table 1 just has determining the densities of our 3 cylinders in them. We're going to record the mass in grams. The height, again, that remember, the height and the diameter and then the calculated radius are all in centimeters, because we have to have cubic centimeters here. And then finally, the density. So like I said, aluminum should be around 2.7, maybe a little bit more. The acrylic should be a little more than 1. And the polyethylene should be around 1 gram per centimeter cubed. So when we figure out what the densities, excuse me, of our solutions are, we should be able to make some predictions about whether these are going to sink when we drop them into the solution or whether it's going to float. So for instance, if we figure out that polyethylene is 1.1 grams per cubic centimeter and a 40% sucrose solution has a density of 1.36 grams per cubic centimeter, is this going to sink or float when we put it in the solution?
Float.
It should float, right? So that is one of the tables you're going to make, where you're going to make a prediction. And as I said earlier, we don't have to do this. We don't have to finish the whole thing tonight, because some folks had a hard time getting all the solutions made. You can do it tomorrow. If you can't finish it tonight, what I would suggest is making your 6 solutions, covering them with some saran wrap or some plastic wrap, something like that to keep things from floating in there. It'll also keep some bacteria, which would just love to get a big glass of sugar water and just go crazy. So just don't put them in the fridge. Why would putting them in the fridge be a bad idea?
That would artificially change the density of the water.
Not only would it change the density of the water, but your solutions that have a lot of sugar in them probably would crash, meaning they would precipitate. The sugar that's dissolved in there, the cold water wouldn't be able to keep them in solution, and they would just crash out, and then you'd have to redissolve them again, and that's a pain. So you want to do your measurements at room temperature. All your measurements should be at room temperature. So the water you use tonight shouldn't be cold. It should be at room temperature. It can be a little warm, that's fine. Especially for making the solutions with high sucrose content. If you want to use warm water, that's a great idea. But once you've made your solution, let them cool down to room temperature before you determine the densities of them. Because what happens to the density of water as the temperature goes up? Anybody know?
It's more dense
Okay, why do you say that?
because ice floats.
But ice is cold, isn't it?
Right. So as the temperature increases, the density would increase.
Okay,
Oh, you,
anybody else have an idea? I see where you're thinking, where you're going with that. Okay. Does anyone think it's the opposite? Nobody? It's actually the opposite. The density actually goes down. So the density actually goes down as the temperature goes up. And that may seem a little confusing, right? Because as you said, well, ice floats, right? I mean, I can prove it right here. You see the ice floating. Why ice floats is because when water freezes, it actually changes its structure. And we'll learn a little bit about the structure of water, because I mean, I find the structure of water fascinating. I'll be boring you to death about water during this class, believe me. It's only the most important thing in the world. So when water freezes, it actually changes its structure, and the water molecules push apart a little bit in order to establish the crystal. And so the density goes down. But actually, as you increase the temperature, the density also goes down, because as you increase the temperature, the water molecules start moving faster. And as they move faster, they actually increase the volume slightly, because they, as they spin it, as they move around a little bit faster, they bump into each other a little bit more, and the volume slightly increases. And so if the volume slightly goes up, the mass doesn't change, but the volume goes up a little bit, the density is going to go down. So that is the case. So I'm not surprised that you thought it was the other way around, but it's just because ice is weird. Ice has a lot of really cool properties. So you want to make sure that it gets to room temperature. So this is how we're going to make the different solutions. So how we're going to determine the densities, we're going to start with water. Water we're going to treat as our 0% sucrose. Why? Because, well, it doesn't have any sucrose in it. So what we're going to do is we're going to take, oh, let me grab my graduated cylinder. Already has some solution in it from last night. So this is the graduated cylinder. Why is it called that? Well, because it has graduations on it, as you can see, and it's the shape of a cylinder. There you go. So what we're going to do is we're going to determine the mass of this empty, right? And then we're going to add 5 milliliters of water. So 5 milliliters, this is a 50 mil cylinder, and there is a major, actually, let me grab something dark because it's kind of hard to see. This is one of the things I recommend when you're trying to determine the volume of something, is that you have a dark background to look at it. So it doesn't really make a whole bunch of difference here, but believe me, in person, it's much, much easier. So you can see that there are major marks for every 10 mils, and there's a smaller mark for every 5. Hopefully you have your own cylinder right now. So what we're going to do is put 5 mils in there, and we're going to, so you're going to have to make an estimate for yourself, like where it hits the 5 mil mark. We're going to use a transfer pipette, which I should have grabbed. Let me grab that. This is a transfer pipette. So hopefully you have one of those in your, you should have a bunch of them in your box. You should have at least 5 or 6 of these. These are great. So they're used for transferring liquid back and forth. So what we're going to do is you're going to take some water up with the pipette, put it into the graduated cylinder, and then when it gets to 5, stop. When you're measuring volume, you want to make sure that your eye is right in a line with the marks on the cylinder. Because if you're looking at it from above, you're not really going to be able to see it very well. If you're looking at it from below, you're not going to be able to see it very well. You want to be right in line with the volume. So if you think there's too much in it, you can actually use the transfer pipette to suck some of the liquid out until it gets right to 5. Then we're not going to do this on the balance. We're going to turn on the balance, measure this thing empty. Then we're going to add 5 mils while we're looking at it like this. Measure the mass, and then add 10. Measure the mass, add 15. We're not going to take any liquid out. We're just going to keep adding liquid to it. So we're going to measure the mass at 5 mils, and then 10, 15, 20, and 25. So at each one of those, we're going to measure the mass. And then we're going to plot them in order to determine what the density is. So I'll show you how that's going to work. So for each one of our solutions, starting here with water. We take we measure our 5 mils. We measure the mass of the solution in the graduated cylinder. We should have the mass of the cylinder empty by itself. And then we're just going to subtract the mass of the cylinder to just get the mass of the liquid. And then for the 0, the 10, the 20, the 30, the 40, 50. So what are we going to do with that information? How are we going to use this information to get the density? Anyone tell me how that works? What are we actually going to plot? What's going to be on the x-axis? What's going to be on the y-axis? We'll start with x. What's going to be on the x-axis here? Remember, the x-axis is the independent variable, the one that we change, and the y is the dependent variable, the one that changes depending on what x is.
The solution would be the X?
What about the solution?
Like
What if-
whether it's like water and stuff, or no?
The volume?
Okay, so we put the volume here in mils. And what goes in the dependent?
The mass of the
The
solution.
mass, that's right. And why is that? That is because we are determining what volumes we're going to measure. We determine we're going to measure 5, 10, 15, 20, 25. We could measure 6, 12, 18, 24, 30. So we're determining what volumes we're measuring. So that is the independent variable. So the mass is dependent on whatever volume it is we choose to measure. So if we choose to measure 6 mils instead of 5, obviously the mass now is going to be different because we decided to measure a different variable. So when we plot these, so we're going to, plot it for 5, 10, 15, 20, 25. So we're going to get data that should look something like this. Right? So as we get more volume, the mass should increase. What's going to be the slope of this line?
Linear.
We should get a linear fit, exactly, because there's a direct dependence of the mass on the volume. Excellent, that is true. We should get a linear fit. What will so the linear, remember, when we get a linear fit, we get a equation that says y equals mx plus b. Remember, we did that with our graphing lab last week. Now we're finding out why we did that graphing lab last week, because we're going to use all those lessons we learned in an actual real life example here. So y is the mass. X is the volume. Plus b is where it hits the y-axis. What is m? What's going to be the value of m?
The slope.
And what is the slope going to tell us? The slope's actually going to tell us something very important. Just think about, what does the slope of the line mean?
Is the density?
It's the density. That's right. Why is it the density?
Because density is mass over volume.
Exactly. Excellent. Right. Since we're literally plotting mass versus volume, and the slope, m, is always the change in y over the change in x, right? Well, since y is mass and x is volume, the slope is going to be mass over volume. What's mass over volume? That's the density. So the advantage of doing it this way, we could calculate the density of each one of those. At 5, we could calculate the density at 5 and at 10 and at 15 and at 20 and 25. We could do that, but it's much more accurate to use all the data to determine what the density is. So we're going to use all of that information. And so we should get a very good line. We should get a linear line. And what should we get as a slope for our water? What should the slope of the line be when we're looking at water? So the very first one we do is going to be the 0 sucrose, or water by itself. What should the slope of the line be when we plot the mass of the water versus the volume of the water?
Just flat?
So we could increase the volume all we want and the mass won't change.
Oh, no, it would be linear still.
Yeah, it'll still be linear, but what will the slope be? What will the actual value of the m be?
1.
1, exactly. We should have a perfect 1-to-1 relationship between the mass in grams and the volume in milliliters. It's super important when you're plotting something that you have the units there. Because if we just have mass versus volume, we don't really know what the slope means, because we don't know what mass is. Is the mass grams? Is it pounds? Is it gills? Is it carats? I don't know what the mass is. But if we plot mass in grams versus volume in mils, I know exactly what the slope is. It's in grams divided by mils. That's the volume. And so with water, since we know the density is 1, the slope should be 1, or pretty close to it anyway. Excellent. So what we're going to do is we're going to plot all of our data on that same plot. So we're going to have water, and then we're going to have 10% sucrose, and then we're going to have 20% sucrose, 30% sucrose, 40% sucrose, and so on. We should get a bunch of straight lines, all with slightly different slopes. And the slope should increase as we increase the amount of sucrose. Why should the slope of the line increase as we're doing grams over mils? Why should the slope of the line increase when we add more sucrose?
Because the density is increasing as well.
That's right. The density is going up, and that should be reflected in that. I mean, we're not going to see huge differences. I mean, the 10% sucrose is not going to be twice as dense as water or anything, but we should be able to tell them. We should be able to tell them apart. And so the point of putting them all on one plot is that basically you can see that. You can see how all of them look fairly similar to each other, and that they're all straight, but the slopes are slightly different. What should the y-intercept be? So when we do y equals mx plus b, so b is the y-intercept, what the value of y is when x is 0. So when the volume is 0, what should the mass be? When I have no volume, how much mass should I have?
0.
0, that's right. If I don't have any volume, shouldn't be any mass either. So that's actually a correction we're going to do. And if you remember what we did last week, we actually forced the line to go through 0, 0, which is x equals 0 and y equals 0. We're going to do the same thing this week, because we're not actually going to measure the volume of 0 mass and 0 volume because, well, we can't really do that. You just have to assume that that's the case. So we're going to basically force our data to go through 0, 0. And that'll be like basically like one of the points in our plot. Okay. So this is how we determine the density of each one of our liquids by looking at the slope of that line. Oops, need my mils and grams. And so the best fit line, you can see right here with y-intercept equals 0. So we're going to force that to be the case. So for 0, or just water, the equation will be something like y equals mx. Now, there's not going to be any b, right? Because y-intercept is 0. So we should, for the first one, we should get something like y equals like 1.01x, something like that. That number right there is the slope of the line, and that is the density in grams per mil. And this should increase as we go to the bottom. I can't remember exactly what your 60% should be. You can actually, you can look these up. I mean, these have all been determined. See how close you are to the real amount. We know what water's supposed to be. And so this should go up, let's say like 1.2, 1.4, 1.6. I mean, I don't know what they're, something like that. What are we going to do with this information? The density versus the percent sucrose. What are we going to do with that? How do we use that information in the last exercise when we're actually trying to figure out what the percent sucrose is in our liquid? What do we do with that data?
We're gonna plot them.
That's right. We are going to plot them. What are we going to plot? So if this is my plot, what am I going to put in my X? What am I going to put in my Y? Which one is the independent variable and which one is the dependent variable?
Y is dependent and X is independent.
So which one is the independent variable here? Is it the percentage of sucrose or is it the density? Which one is the independent variable that we've changed?
Sucrose.
That's right. It's the percent sucrose. So X is going to be the percent sucrose. And we're going to plot 10, 20, 30, and so on. And then Y is going to be the density in grams per mil. So we should see, I don't know exactly what the line is going to look like, something like that. So when you measure the density of your beverage, whatever it is, you're going to determine it the same way as you did the 0, the 10, the 20. You're going to take 5 mils of it, 10 mils of it, 15 mils of it, figure out the mass, plot the mass versus the volume, figure out the density. Then once you have the density, let's say your density is, I don't know, 1.42 grams per mil. Let's say that's what you got. So now all you need to do is go up here to wherever 1.42 grams is on your plot, go across to where 1.42 crosses X and then go straight down. And you see that, wow, 1.42 grams, that's a lot of sucrose. That's like something like, 55% sucrose. I don't know what drink that would be, but that would be, pretty intense. So that's how you use this information, percent sucrose versus density, to actually figure out what the sucrose concentration is. We're actually doing it in reverse. by figuring out the density, you go backwards and then figure out what the percent sucrose is. By calculating Y, you then figure out what's X, okay? So all of this, like I said, all this is stuff you can do tomorrow if you don't want to stay up super, super late, I understand. So sinking or floating, now that you know all the densities of your solutions, you've calculated what the densities of your solids, then you just make a prediction. Is it going to sink or is it going to float? So just put, oops, let me go back. Just put S for sink or F for float, okay? And then actually do the experiment. So you'll have your 7 solutions. One of them's water. And just take these things and toss them in there and see, do they sink or do they float? And then see if they agree. Now, do you think the shape of these will have any effect on whether they sink or whether they float? What do you think? Does the shape affect whether something sinks or floats?
No.
No.
Really? How come boats don't sink then? A battleship is awfully dense, isn't it?
The surface tension of the solution that you're in.
Surface tension is definitely one.
Mhm.
But the shape is also super important. Boats are shaped like that for a reason.
It increases the surface area.
Exactly. So, yeah, if you have like a leaf will float on the surface of the water, right? Even though a leaf has a density greater than 1 gram per mil because of the shape. So if it's large and flat, it'll actually, make contact with enough water that it displaces more water than its actual mass. And so it floats. Same with like a battleship. If it displaces more water than its own actual mass, it'll float. So it could be that the shape of these, I don't know, to be honest, whether the shape of these has any effect, but we will see. But don't feel bad if you predict that something will sink and it doesn't, or the other way around. Because the shapes of these things do affect whether or not they sink or float. So don't freak out if you're wrong about some of these. So then finally, I kind of went over how we're going to determine the sugar content. This is the last table you're going to fill out. So figuring out what exactly the amount of sugar in the beverage is. What's wrong with this table? There's a mistake here. Anyone spot what it is?
Do they want to know the mass of? Oh, never mind.
Yeah, we're just going to put the mass of the cylinder. It should be the same. If you're using the same cylinder, it should be the same mass. You're determining the mass of the beverage. Nothing wrong with that. Nothing wrong with the mass of both the beverage and the cylinder. Something else is wrong.
The percentage of the volume.
Right. There's no such thing as 5% mils. Right. So there shouldn't be a percent there. The volume is 5, not 5%. So these shouldn't be there. That's a mistake. And I think why it's there is because we're going to be using the percent sucrose values to determine what our sugar concentration is. So I think whoever wrote this sort of got ahead of themselves a little bit. So we've already gone over how are you going to determine the percent sucrose. You're going to do that by plotting the percent sucrose versus density. And then figuring out what that relationship is. So excellent work. Okay, any questions before we get started on how we're going to do the experiment tonight? So give everyone like a couple minutes to get their stuff together. And actually, the first thing we can do is do the first part, which actually you don't need to have the goggles on or anything, and actually measure our cylinders. So why don't we just start with that? So hopefully everyone's got their camera on. So if you have any questions. So remember, what you want to do is, in this part, measuring the height is going to be fairly straightforward, because you can just, put the ruler next to it and kind of figure out the height. What's a little trickier is measuring the diameter, because remember, with the diameter, you want to be right in the middle. You want to measure the distance across the circle in the middle. That's kind of hard to determine if you're actually in the middle or not. So you're going to be a little bit off. Like I said, when I did this last night, my measurements were off a little bit. I got a density for aluminum of 3.1 grams per centimeter, and it should be 2.7. But that's not too bad when you're dealing with, this sort of precision equipment and these old eyeballs. So remember, you want the first two digits are going to be significant, because you're going to see that it's definitely, more than 10, more than 11, more than 12 millimeters. Remember, each one of these small markings is a millimeter. But you have to determine whether or not this, which is really hard with my big fat fingers in the way, is more than 12, less than 12. Where is it between 12 and 13? That's only you can decide that, and prevent forest fires, apparently. So don't feel weird or bad or anything if everyone's saying it's like 11.9 and you're saying no, mine's 12.2. Is there something wrong with me? Yeah, these things aren't going to be machined to that kind of precision. So not every one of these is going to be identical. They're going to be really close, but they're not going to be identical. So don't worry if your measurements aren't exactly the same as everybody else's. Everyone's an individual. But when you do your calculations, let me put up a screen here. When you do your calculations, you should get a volume around between around 1.2 to 1.5 cubic centimeters. It should be somewhere in that vicinity. So remember, don't use millimeters. So if you measure something at 12.0 millimeters, how many centimeters is that?
120.
120 centimeters?
Hmm.
Which one's bigger, centimeters or millimeters?
Centimeters, sorry.
Centimeters are bigger,
It
right?
should be
So the number of
1.2.
centimeters should be smaller. So the decimal should go the other direction. So 1.20 centimeters. And we include this 0, right? Because you decided that the edge of your cylinder was right on the 12. So 12.0. So you include this 0. So you should have something, so you should have, remember, volume is pi times the radius squared times the height. So this will be in centimeters. This will be in centimeters. And you multiply it by centimeters since it's squared. So that gives you centimeters times centimeters times centimeters, or centimeters cubed. And if your calculator doesn't have a pi on it, just use like 3.14159. That's close enough. That gives you 6 significant digits. So that should be more than enough. I think pretty much every calculator is pi. Actually, no, I'll take that back. My calculator doesn't have pi on it, so I have to use this. I can't even afford a calculator with pi on it. All right, so I'm going to move my camera to my workspace, and then we can start working on making our solutions. Okay. So let me just pause first. First of all, any questions so far about doing these measurements? They seem fairly straightforward. I think the key thing is just to use centimeters rather than millimeters. Man, you guys are quiet.
I have a question.
The Wednesday group is so much more rambunctious than you guys.
You said that when we're measuring in the centimeters, we
Yes.
want to go towards the number that is more exact, right?
Don't quite know what you mean by that.
Like you were saying, like if it's measuring at like 1.2 centimeters,
Mhm.
we can put one, because that's not necessarily exact. The 0.2 is not necessarily exact. Right? That's what you were
Well,
saying earlier.
when you're, so if it's, so here's the ruler, right? So you can see that it's got each tick mark is a millimeter. So if you think that it falls exactly on 12 millimeters, then you have to write down 12.0 millimeters. So then when you convert it back to centimeters, that's 1.20 centimeters. So the thing is, with any measurements we do in chemistry or physics or really anything, why significant digits are so important is that we want to conserve precision. So if you take the time to measure that precisely, your results should reflect that. So if someone says 1.2 centimeters and you say 1.20 centimeters, I know that you measured yours more precisely, and I would believe your number more than the 1.2. That's a more important number than 1.20. That gives me more information. Because 1.2 tells me it wasn't 1.1 and it wasn't 1.3, but 1.20 gives me additional information that I don't have. All right, let me move my stuff. All right, so you can see my sweet setup here. So I figured what I'd probably do is just, everyone should have their cameras on and their goggles. And you're saying to yourself, hey, I'm going to look like a dork if I wear my goggles. And yes, you are. So, but everyone's going to look like a dork. So you shouldn't feel bad. I realize that, you may not think it's important to wear goggles for dealing with sugar and water. I understand. But later, when we're dealing with acids and bases and fire, it's non-negotiable then. Okay. So get used to wearing them. All right. So how do we make a solution? Okay, so I'm going to make the 20% sucrose solution because I made the 10% last night. So I figured I'd do something a little different. So what we have to do is we get one of these, one of our cups looks like this, and we're going to mark them with give like a wax pencil or a Sharpie or whatever you've got. You just put a piece of tape on it and write on that. So you're going to want 10, 20, 30, 40, 50, 60. So, all right, 20. Oh, yes, got a marker over here. Oh, no, I don't. Damn it. Should have brought a marker down. All right. All right, 20. Okay. So here is your, I don't know what your particular balance looks like. Mine looks like this. Yours may look different. Yeah, I think those are the new ones. Yeah, I got one of the old ones from last term. They all work the same. So there's two buttons on them, one on the left, one on the right. The one on the right turns it on. So give it a second to let it go. The one on the left tells you what units. So what's really important is that it says grams. Can you see that? Where? It should say grams. Now these things were made for a lot of different stuff. These are actually jewelry scales. So if it says CT, that's actually carats. So if your significant other bought you a ring and you're sort of wondering or not whether they actually love you, well, then you can just measure the actual carats there. They might be liars. So the other thing is GR. GR stands for grains, which is like a really old timey English unit of measurement that I don't know, some people still use for some reason. So you just want just G, okay? It's also super important to have a flat surface. It's got to be flat. As you can see, it says 0 when I have it on a flat surface. And the minute I pick it up, it starts giving me all kinds of weird numbers, right? It's just jumping all over the place. So it needs to be flat. And when you make a measurement, if you just blow on it, you'll see it makes a big change. So you don't want to have a fan over on top of it, or you don't want to have it by an open window or anything like that. Like if we were in the actual lab, you would see that a lot of the balances we use are inside of a plexiglass box to keep airflow from messing up just doing that makes it change. So the other thing we need to learn about is something called tearing, T-A-R-E. Anyone know what tear is?
It's like,
Sorry?
it's like resetting the balance.
It is like resetting it. So what you want to do is, if it doesn't say triple zeros, you hit the right button again. So the power button, you hit that again. Don't hold it down, just hit it once. And it should reset. The other really, really important use of tear is, if I put my cup on it, I get around 10 grams or so. But then when I hit the tear, it goes to 0. Now that's really helpful, because now when I add a solid to this, it's only going to measure the mass of the solid, not the mass of the cup. So it'll automatically get rid of that for us. So an important thing to remember. So then when I take the cup off, now it says minus 10 grams because it's been tared. So now I have to tear it again. Okay. So I want to measure 50 grams, sorry, I already did that. 50 grams of water. So I put my cup on. I'm going to tear it to 0. Now, here is my filtered water that I've sort of left out to get to room temperature. You should have that. You don't, if you're using tap water, that's okay, but it should at least be room temperature. Although tap water is going to have all kinds of stuff in it that you don't want. So filtered water is fine. Bottled water is probably fine. But the most important thing really is the temperature. This has been sitting out for like 24 hours. So it is definitely the same temperature as my room here. So how are we going to measure 50 grams of water? Do I just dump this directly into the cup? Maria says, no, I shouldn't do that. She's absolutely right. Yeah, you don't want to take this and just dump it right in there, because if you splash it over, it's going to splash onto your electronic component, and bad idea. So what's close to, what volume of water can I measure in my graduated cylinder that I know is going to be pretty close to 50 grams? What do you think?
Like around 20-ish milliliters or more.
Nope. What's the density of water?
50 ml. I mean,
50, right. It's around 1, right? At room temperature, the density of water is precisely 1 gram per mil. So a little colder than room temperature in here. And I'm not going to be able to measure the volume as accurately as this is going to be able to measure the mass. So I'm not going to be too fussy about getting exactly 50 in here, but I'll pour about 50 in here. Then I'm going to pour from my graduated cylinder into the cup and see what the mass is. And it's a little more, 51.57 grams. So that's where I use my transfer pipette. I'm going to take some water out of here until I have 50 grams left in it. Okay, I'm just going to pull some water out. Pull some water out till I get a little bit less than 50, and then I'll put some back by squeezing it till I get exactly 50. Now,
Professor,
don't worry about getting 50.00.
I have a question. So
Yeah.
when you know how we have to weigh the cylinder first, that would go on the mass of cylinder, right?
Nope.
No?
I'm just making the solution right now.
Okay.
Yeah. I'm just going to make the solution first, and then I'm going to do the calculation. So, ooh, I got it right on. So I got 50.00 grams. So pull some out with your transfer pipette till you have less than 50, and then just go drop by squeezing it till you get 50. Okay, so now I have precisely 50 grams of water in there. Now I want to measure my solid. So to measure the mass of a solid, I use one of these. What's this?
It's a weighing boat.
That's right. Excellent, Jaden. How come I can't see you, Jaden?
You could see me now.
No. There's a whole bunch of you without your cameras on. Remember, we're going to do cameras on for lab. So I can see how, there you go. So I can see how pretty you look Oh, Christian, man, you look like a total stud ball with your goggles on. Awesome. Yeah, this is called a wave boat, which is kind of a, I don't know, I guess it's called a wave boat because it floats on the water. So what you want to do with this is you put it on the scale, empty, and then you tear again. So I just hit the power button again, and it goes to 000. Now, as you can see, I have brought more than enough sugar for tonight. So you want a clean spoon. Here's my clean spoon. Take your scoop. Now, gently tap. See if I can get the zoom in a little bit. You want to gently tap. Don't just dump it all in at once, because if you get more than 5, it's really kind of tricky to get the sugar out. It's much more easy to add a little bit more than it is to take some out. So you just keep gently tapping, gently tapping. Now I'm making the 20%, so I want 12.5 grams. So I'm probably going to use more than 1 scoop. Yeah, 1 heaping teaspoon is around 6 grams. So now I'm going back for some more.
Professor, I have a question.
Mm-hmm.
Can we use the raw brown sugar, or it has to be that
It
type
should
of
be the
sugar?
white sugar, because the raw brown sugar has molasses in it. So, I mean, if that's all you have, then that's all you have. So one of the questions in your report is looking for sources of error. So you would write that down as a potential source of error. Because we're always on the outlook for trying to figure out, any scientist is always looking, because you're going to make errors. There's no way you can't. It's impossible not to. And the vast majority of them aren't your fault. They're just like for instance, there's no way to measure something as accurately as you would like, that sort of thing. What we want to cut down on are so-called systematic errors, which we make over and over and over and over. Like if I go a little bit over or a little bit under the mass on some of these, that's no biggie. If I make the same mistake in the mass over and over and over, that compromises my experiment. So if you go a little bit over on one mass and a little bit under on the other one, that's totally fine. Those little errors tend to sort of work themselves out. So I got exactly 12.50 grams. So I take my cup that has exactly 50 mils of water in it. And the nice thing about these boats, other than you can get hairs in your, is that you can bend them like this. See how you can bend it? And that makes a nice little, I don't know what you would call it. It makes it easier to pour this. It makes like a spout that you can then pour this directly into the water. So you don't spill any. So I pour it in there. And then you also want to tap this, because there may be some sugar still stuck to it. I check it. There's no sugar in there. Good to go. So to dissolve it, then I just get my second stirring spoon, and I'm just going to stir it. And I don't have a microwave down here, so I'm just going to stir this and stir it and stir it and stir it. How am I going to know when everything's gone into solution? When do I know
Here.
when my solution's finished? In other words, when can I stop stirring this stupid thing?
When the water is clear.
Right, yeah, the water's clear. I don't see any more crystals. So like I said, when you're making like the 40%, the 50 and the 60% in particular, it probably won't go into solution just by stirring it alone. You're probably going to have to either use some warm water, or you can just throw these cups in the microwave and nuke it for like maybe 5 to 10 seconds. I would not heat it any more than that, because these cups are probably going to melt in the microwave if you leave them in there too long. Even if they get a little misshapen, that's okay. Well, you don't want it like to melt a hole in the side of it, and then all your solution runs out and screws up your microwave. So because sucrose is a white crystal, and I've got as you can see, I've got like sort of like a white diaper paper here to clean up after any spills. I'm not really going to be able to see white against a white background very well, but I do have this black container, and so I will look through against the black, and I don't see anything. So I think I've pretty much got all that in solution now. Cool. Now remember, you're going to make 6 of these. So you can make all 6 of them at once, which would probably be the best thing to do. I am not going to make all 6 of them tonight. The recipes are in the instructions, as you can see. So what I'm going to do now is go over how to measure the masses. Now that I have my 20% sucrose solution, how am I going to measure the masses of them? I start with a clean cylinder. I want this to have no liquid in it at all. So if it's had any liquid in it, I can just give it like a flick. This is my wife's office, so I can mess it up a little bit. Don't tell her I said that. Okay. So I get rid of the liquid that's in here. And now is where we measure the mass of the cylinder, okay? So I tear my balance. I put my empty 50 mil graduated cylinder on it. And I measure the mass, 2945. Okay. Then I take it off. Now, with my 20% solution, I take my transfer pipette and I add 5 mils of my 20% solution to this. And here's where you want to get down and line up. So you can see 5 is, so the 10 is here. So there's the 10 mark. So the 5 is halfway up. And you can probably see this better on your own. But the 5 mil mark has a little bit long, a little bit wider than the rest. It goes 1, 2, 3, 4, and then 5 is a little bit wider. So I'm going to take my transfer pipette and start adding water. So start adding my solution, my 20% solution. And again, you have to keep it parallel with your eyes so you can see the 5 mils better. have some liquid that's stuck to the side, just give it a tap to get it all down there. That looks pretty close. So that's pretty close to 5. I don't think I'm going to get it much closer than that. So I would call that 5.0, right? I really can't make it any more. I can't get any more significant digits than that. 5.0. I can't say 5.00 because there isn't sufficient markings on this to let me tell the difference between 5.0 and 5.1. So 5.0 is as good as it gets for me. And then I just transfer it back to the balance and I just read the mass. Okay. Then I don't dump this out. I just add another 5 mils to it till I get to 10, doing it the same way. And 5 mils is about 3 good squeezes of your transfer pipette, 3 or 4. 2 if you give it a really hard squeeze. Okay. And one thing I didn't mention in the, we start to get more and more volume. What's something that happens to water when you pour it in a cylinder like this? Is the line of the water going to be completely flat?
No, the meniscus curves slightly.
Ah, Sonia, if only I could see you, then I would be telling everyone what a genius you are. Yes, she's absolutely right. There's a meniscus. What does that mean? Could you explain what that is, Sonia?
It's been a while since I studied this, but I think that it has to do with the surface tension of the cylinder and water. So the water is actually held up by the surface tension that it's being grabbed by the object that it's in.
Yeah, water, yeah, I couldn't have said it better myself. Yeah, water has a very special property. It's very sticky to itself. And we'll learn about that when we talk about shapes of molecules. Water is very unique in that way, that it sticks to itself better than hardly any other molecule does. And so that's why you have something like capillary action. That's why redwood trees can grow to be over 1,000 feet tall. The only reason they can do that is because water sticks to itself and forms basically a cylinder of water that you can pull up from the ground all the way up to the top of the tree, because the water molecules are sticking to each other. And the same thing is true here, that it's not too much, but you can see that it's not quite flat all the way across, and that the water curves up on the sides of the cylinder a little bit because they're sort of sticking to each other, pulling themselves up the sides of the cylinder. So we want to look at the bottom of the meniscus. So you want to look in the middle, not on the sides. So look at where the water is in the middle of the cylinder, not on the sides. It'll be slightly higher on the sides than in the middle. So we call that the bottom of the meniscus. Great job. So now I've got about 10 in there, 10.0. And measure the mass again. And then I just keep going. So now I've got 10, then I'm going to do 15, 20, 25. Then I am finished. So once I've done that, then we will go over how to plot the data, because that is super important. Any questions so far? How are people doing?
I got a little confused. Since you're only using the 20% solution, is that we're doing that for every
You do that
solution?
for every single one. So
Okay.
water, 5%, 10%, 20 to 34. So it's going to take a while.
Okay.
So that's why I'm saying you may want to make your solutions tonight and then do the measurements tomorrow, if you don't have time. So if you want to stay up till late, then you can do that. There's 15. So another thing I want to mention is one of our students, one of your classmates last night made a really good point. They had printed out the outline for the report, and they were making notes on it and wondered if she should do that. The answer is no, you shouldn't do that. The outline for the report is for the report, not for taking notes on. You should have a lab notebook that you make all your notes in. So, I'm writing my notes in a lab notebook. So then when it's time to write my final report, I will use the notes that I've taken to write my final report. They're two totally different things, okay? Probably hear my dogs upstairs. Someone must be walking down the neighborhood. Okay. So 20. Yeah, so the rate limiting step here is making the solutions. That takes the longest time. Once you've got them all, doing the measurements are actually pretty fast. Okay. So I'm going to pause again and go over back to the desk. And we'll do some plotting. Okay, and we're back. So while you're making solutions or not making solutions, figured I will go over how to handle the data that you've collected. So we'll go back to Google Sheets, which is what we used last time. So here's Google Sheets. Here's my data from last night. So I'm going to just get rid of this and basically show you how to put the data in. So remember, our X is going to be volume, and the X axis is always the first set of data to go in. So here's my X, 5 mils, 10 mils, 15, 20, 25. So that goes in first. The next would be the mass of my water, 5, 10, 15, 20, 25. My 10% sucrose that I did last night. And then now I'm going to put in my 20%. And then you calculate the mass of the solution by taking the mass of the solution plus the cylinder, subtracting the cylinder. All right, so for 5, I got, let's see, 5.31. And then 10.96. And then 16.6. 22. It was 16.60, but if I put the 0 in, the computer automatically spits it out. So it won't affect the calculation. 22.23 and 27.34. Now it's best to do all these at the same time because I don't know if I have exactly the same conditions in the office that I did last night. The humidity may be different, the temperature may be different. So it may not be, it's not the wisest idea to compare data from an experiment I did yesterday to what I'm doing today, because I'm not doing it, I'm not collecting my data all at the same time. That may not seem like a big deal, but believe me, when you're doing like, you know, big experiments, stuff like that is important. So if you really wanted to compare, you would do them over again, but I'm not going to do that. All right, so this is how I handle my data. So I've got my water, 10%, 20%. So I am going to select the data I want to plot, starting with the headings, because I'll show you in a minute, that'll be very helpful. All right, so that's what I want to plot. I come down to insert, if you remember, chart. And what kind of chart do you want? A line chart? I do not want a line chart. I want a scatter plot. Down there, that's what I want. Okay. I'm going to move it over here. And I can also make it a little bit bigger so I can see it a little easier. There we go. So I can see the points a little bit better. All right, there we go. So some things I want to do. First thing I want to do is increase the volume. See, it only goes to 5. I want it to go to 0. So I'm going to double click on the 15 on the x-axis. And horizontal axis. Here we go. I want the minimum value to be 0. There we go. So now you can see I've got, where's my marker? Oh, here it is. You can see that now I've got 0 in the as the minimum for x, which makes things a little easier. So when I look at the y-intercept, it'll be a little bit easier to see. Also notice that these points are pretty close together, which makes sense because there's not going to be a whole lot of difference in density between 10% sucrose and 20% sucrose. It's not going to be a massive difference. So the next thing I want to do is draw a straight line through my data. How do I do that? Well, click on, so the 0% is blue, the 10% is red, and the 20% is this sort of burnt umber, or whatever you would call ochre or something. So we're going to click on one of the blue points. So I double click on the blue point, and it goes to series. You see series here. Series. So I go scroll down. What do I want from my series? Well, I want a line. I want a trend line. So I click, yes, I want a trend line. What kind of trend line do you want? Well, I want a linear one. because I'm expecting a linear relationship between the volume and the mass. That is what I want. I want to show the R squared. Sure, I want to see how close. I want to see how close to the line. Oh, you can see it's perfect. R squared equals 1, meaning it's a perfect straight line. Because, you know, you're dealing with a professional here, ladies and gentlemen. So, but I want to see the equation. That's the whole point, right? That's under label. So label, use the equation. So there you go. So now I have for 0%, which is just water, there is my equation. Y equals mx plus b. There's the equation right there. So the m is 1.01, and the y intercept, the b, is plus 0.224. So one of these things is good, and the other one's not so good. So the slope, that's really close to 1, right? I'd say that's about as close to 1 as you're going to get. That's the actual, that's what I've calculated as the density of water. 1.01 grams. So I've got grams over here and mils over here. Grams per mil. So that's pretty good. This is problematic though, because as I sort of explained before, we really want this to go through 0, right? We don't want a y-intercept because at 0 mils, there shouldn't be any mass. According to this, if I have 0 mils of water, it will weigh 0.224 grams. And that's obviously not true. It should weigh 0. So what are we going to do? I'll show you in a second. First, let's do the other two lines. So I click on the red this time to get my 10%. Double click on the red. Clicked on 20. Let's do 10. So I want a trend line. I would like the R squared, and I want to see what the equation is. So same thing here. And again, R squared of 1, because, you know, what can I tell you? And so here you can see that the slope now is higher than just plain water. Slope's a little bit higher. So instead of being 1.01 grams per mil, now it's 1.06 grams per mil. It's a little bit more, and it should be a little bit more, right? But we also have a y-intercept. There's the y-intercept there. Not as bad as the one for water, but still really shouldn't be any. So let's do 20%. So we just scroll back up here. So these are my series. This just means these are the different y values. So my y values are 0, 10, 20. So now I want to do 20. And you can change the color if you want. There's a whole bunch of different ones here. I kind of like that ochre one. It's a very 60s kind of vibe to it. So I want trend line. Again, I want it to be linear. I want to see the R squared. Oh, why isn't it giving me an equation this time?
Click on custom where it says label.
Oh, I forgot. Oh, excellent. You're right. Very good. Use the equation. There it is. Okay. Thank you. So you can see that now there's my new equation. It's a little different. The slope now is 1.11 grams per mil. And this time my y-intercept is actually negative. So it's a little bit less than 0. It's pretty close to 0, but it's a little bit less than 0. So that's also problematic. So let's deal with that, because what these slopes are, this one, and this one, we're going to call uncorrected. These are uncorrected because we haven't corrected for a y-intercept of 0. So if you remember, hopefully some people will remember from last week, how do we deal with that? We dealt with it by using a function in the spreadsheet called linear estimate. Remember that? It all comes flooding back to us like happy memories at the beach as a child. Yeah, so we put equals lin est, or linus, depending if that's how you want to do it. It's the best fit linear trend. Yes, we already have a linear trend, but we don't want the y-intercept to be whatever it's giving us here. We want it to be 0. So how do we do that? So we put in lin est, bracket. Now we need to show the computer where our X and Y data is that we're interested in. So we're going to do the water first. So you select the Y data. Here's my Y data. And you can see that it fills it in automatically. There's my Y data. So I put lin est bracket my Y data, comma, my X data, comma, false. If you remember that. So I'm going to do that here. So there's my Y data. I put a comma, and then I tell it where the X data is. The X data is always going to be the same because everyone has the same X data. It's 5, 10, 12, 15, 20, 25 mils, right? Comma, false. And then parentheses, fill in my bracket. And then I just hit enter. Okay, let me erase that so you can see. Okay, so see what happens. What I have here, this is the new M. This is the new slope. And right next to it, this is the new y-intercept. Well, you can see what it's done for my water data is it's forced the y-intercept to be 0. And that changed the slope slightly. Before I got, so over here with non-corrected data, my slope is 1.01. Now you can see the slope with the corrected data is now 1.02. So it didn't make a big difference, but it did make a slight difference. So now my corrected value for the density of water is 1.02 grams per mil, not 1.01. So, you know, I'm 2% off of the actual value. So I'm going to have to give up my chemistry, turn in my chemistry badge. I made a 2% error. All right, so next let's do the 10 and the 20. Let's move this out of the way. Come on, you. There we go. Move it out of the way a little bit. All right. So I'm going to do the same thing. So come down. So now it's going to be equal linist bracket. Now the Y data for the 10% sucrose is here, right next to it. So I put that in, comma, X data, same as it ever was, right there, comma, false. Hit enter. So there is my new value for the slope for, let's see, 0%, 10%, and then the next one will be 20%. So my new corrected value for the slope for 10% is 1.06, which is the same as it was for uncorrected. So that hasn't changed. So 1.06 is the same grams per mil, 10%. So that didn't change. And that makes sense because you can see that the y-intercept is really close to 0, much closer to 0 than the water was. So it was really close to 0. So when you correct it, it really doesn't change very much. So that makes sense. So I get the same value for 10%. So those are my first two densities, for 0 and for 10. So now we're going to correct it for 20. So again, equals linist brackets. Here's my y data for 20% now, comma, my data, x data, same for everybody, comma, false. Close brackets, hit enter. And that has changed a little bit, actually. I'm a little surprised. Okay, so there's my new value for 20%. So you can see the slope went from 1.11 to 1.10. So notice the slope is went down a little bit. And the reason, because now this time my y-intercept was negative. So when it was corrected, it actually lowered the slope slightly. So that makes some sense. So now my new 20% value is 1.10 grams per mil. So you're just going to do this for 30, 40, 50, 60. So then you should have 7 lines on your graph, because we want to have all of them on there at the same time. And you can also, since you're going to be putting this graph in your report, you want to make sure that you have a label every, so you just double click up here and chart title here, chart and axes titles. So you want to give this a title that means something like determination of sucrose solution density or something like that. So that's the title. So the horizontal axis title is already there. It has volume in mils. That's fine. But the vertical axis, the y-axis, doesn't have a title. So we need to put one in there. So what would be a good, oh, you can see it already has one suggested, mass in grams. Yeah, that's a good one. Mass in grams. So you can see always, so there's a couple things you always have to have on a graph. You have to have axes titles. You have to tell me what it is you're plotting, and they have to have units, because I need to know what units the slope is in. If I don't know what the units are, I don't know what these slopes mean. I have no idea what those are. So that has to have units for both. So volume and mass. It has to have a title. I need to know, like, what the hell is it I'm looking at? I don't know what I'm looking at. So you should have, like, a title, maybe the date, something like that in there. And then finally, the other thing it needs is I need to know what these things are. What are these? So it needs to have something like this that shows me what these points are. And if you have the lines, I need to see the equations. Okay, so make sure you have this included, because that way I need to see what it is I'm looking at. So any questions about how to deal with the data? So you're going to do this exact same thing with your unknown beverage, whatever it is. You could even put that on the same graph if you want to. Any questions on how to plot the data and how to correct for zero y-intercept? So quiet. Is everyone sleeping already? Is that the idea?
Professor?
Yes.
How
Go
do we
ahead.
add the beverage part?
Oh, sure.
This equation, yeah.
No problem. Clear all that out of there. All right, let me move this out of the way. So I would put my 30% data here. And the reason I type this in here, notice that it automatically, when I plot it, it automatically puts the 0, the 10, the 20, the 30. That's really, really helpful. So that's why I put these headings here. And then 40, 50, and then you just put, beverage, bev or something like that. So then when you give the masses here, let's say the masses are, 5.23, 10.67, 15.99. Oops. Then it'll just show up on this on the same plot, and then you just click on beverage over here, or either click on the spot or any one of these spots, select beverage, and then get the straight line fit for that as well. And you're also going to want to correct for zero intercept with your unknown beverage also. Okay.
Okay, thanks.
No problem. Yeah, so for this, you're just going to want to copy and paste it. Yeah. Yeah, so just right click. Oh, I think you can. Where is copy? Copy. Oh, edit. Yeah, copy. So just copy it and then paste it into your report. So here's insert graph from table 3 here. So I would delete this. And there you go. Just paste it in there. Okay, and that's it. Then you're done. So it should have the 0, the 10, the 20, 30, 40, 50, 60, and I think your unknown, or maybe you do your unknown separately. Data table 2. Where does the beverage go? I think maybe you don't. Oh, okay. Yeah, data table 5. So here's where you would put the date. Actually, they do want the data for the beverage separate. So here. So don't put it in the same one. I don't know why.
A different graph.
Yeah,
Okay.
put it on a different graph, but do it exactly the same way. That's kind of stupid. I should have corrected that. There's no, have them all in the same one. Shouldn't make any difference. Okay.
Are we able to request for a word copy of the report?
I'm sorry?
I mean, sorry.
No, I just couldn't quite hear you. You wanted a hard copy?
No, a word copy.
Oh yes, there's a Word copy and a PDF. There's
Okay,
both.
thank you.
Yeah, there should be both in there. Yeah, because some people had trouble with the PDFs, which I completely understand. So yeah, so there's the Word there. There's both, depending on which one you want to use. Any other questions? So you folks who don't have your cameras on, Since next week we're going to be dealing with some serious chemicals, I'm going to want to see your cameras on and goggles on, or I will not be grading your report. Okay? Don't want to be
I sent an email to Carolina asking for them to ship the kit to me.
uh-huh. Oh,
I haven't heard anything back. So I still don't have any of the equipment.
where are you?
New Caledonia?
Oh, right. You're the one on the other side of the world. Sonia.
Yeah.
That may be a while.
Okay.
Yeah,
I'll do my best.
That may be a while.
Okay.
Although for this one, I don't know if you can find a graduated cylinder and
I have everything
That's really
except
all you
the,
need for this one.
Yeah, except I don't have the cylinders that we'd be dropping.
I can
in
send you the measurements I got, and then you could work out the
Okay, I can do the math from there.
do the math
Okay.
from there. Exactly.
Okay, that's perfect. I can do that.
Yep. I'm amazed that your connection is that good from a boat off
Yeah,
the
sometimes
coast of
when
Australia.
I add the video, it's not so good, but I'll go to
right.
shore if
Okay, I understand.
yeah. I just don't want to drop, so that's why I have the video off today.
There you go. Fair enough. So any other questions? So what I would suggest making all your solutions tonight. If you don't want to stay up super late, make your solutions the 10 to 60%, cover them with saran wrap, put them somewhere safe, not in the fridge, and then do this tomorrow morning before you go to work or after you get home. Because tomorrow will be Friday. Maybe you might want to do it on Saturday. I don't know. You don't want to leave these out for too long because, yeah, like I said, no matter how hermetically sealed you think it is, there's going to be some bacteria get in there and yum, yum, yum. How you doing, Liesel? Liesel or Liesel? I can't remember.
It's Lizelle.
Lizelle. There you go.
I'm okay. I'm just a little under the weather, so.
Oh God. Okay. You
Yeah.
haven't got a fever, do you? Don't get the COVID. Don't want you to have that. Did you have your shots? Good job. All right. Any other questions before we wrap it up? Because right now, I mean, basically now it's just a matter of running through. So I think you're familiar. So you're familiar with the procedure and what to do from this point. See? All right. All right, everyone. Oh, who wasn't able to get onto Chem 101 tonight? How many people? I want to see if there's a pattern. So Rosalia? Anybody else? Who else wasn't able to get onto 101? Just one person? Okay, I'm just going to assume it's just that one, and I will see what the connection is with the folks who couldn't get it in last night as well. Maybe everybody has something in common. Oh, you just got in. Oh, there you go. Excellent. All right, yeah. So from now on, that's really how we're going to start the lab. So yeah, if you guys want to take it beforehand, even better. So that'll give us more time to do, but we don't have to sit around waiting. We can actually go ahead and get more done. So if you guys want to do it beforehand, that I have no problem with that. Okay. Anyway, so what I'm going to do is I'm going to post this weekend. I'm probably going to record the lecture for chapter 3 and 4. So we're going to be doing those together. So watch it before class on Tuesday, because we're going to spend like about the first half hour or so taking questions about it. And then we'll have a new worksheet to work on. We'll have more time to deal with it. Okay.